So Coulomb's law calculation. So before you watch this video, or if you've started watching it, pause and rewatch the video of scientific notation calculations, because it's really important that you understand how to do that. So we're using Coulomb's law, which is F equals KQQ over R squared, and we're using that. So here's an example of a calculation. A charge of positive 6 microcoulombs, this is a micro, is 3 centimeters from a charge of negative 9 microcoulombs. What is the magnitude and type of electrical force of attraction? Well, one thing to note is that microcoulomb, micro means that it's 10 to the negative 6. It's 1/1,000,000th of a coulomb. And that's the charge. So instead of saying 6 microcoulombs, I have to say 6 times 10 to the negative 6, or 9 times 10 to the negative 6. And the radius has to be in meters, so a centimeter is equal to 10 to the negative second meters. And the K value is always fixed. It's 9 times 10 to the 11th. So the solution for this. Well, the first thing that I can say is that the two charges are have an attractive force because I have a positive charge and a negative charge. Not really worried about the magnitude right now, just the type. So as long as these two charges are opposite charges, it's going to be an attractive force. So I got type out of the way. Now for the magnitude. This is my equation, and I'm solving for FE, so I can just plug in the values. So K is equal to 9 times 10 to the 11th. The first charge is 6 times 10 to the negative 6th, because it's microcoulombs. I have to convert to coulombs. The second charge is 9 times 10 to the negative 6. Now, remember, because this has a negative here, that doesn't matter in my calculations of the magnitude. Once I figure out that it's an attractive force, I can ignore that it's a negative charge and simply put the absolute values in. And then my R, my distance, is 3 times 10 to the negative second squared. So rather than just writing the square term, because that's so easy to get lost, I actually just write it out twice. This is just, again, to be kind to my future self. Now, the nice thing about scientific notation is that I can take this one step at a time. So we're going to do the exponents first, just the 10 to the whatevers. So I take the 10 to the 11th, this 10 to the negative 6th, this 10 to the negative 6th, and then these two 10 to the negative seconds. I'm just going to do that calculation. So remembering my exponent rules, whatever is multiplied, you add, and whatever is divided, you subtract the exponents. So I take 10, which is my base, to the 11th, plus negative 6, plus negative 6, minus negative 2, minus negative 2. And when I do all of that, it ends up being 10 to the third, because 11 plus negative 6 is 5. 5 plus negative 6 is negative 1. Negative 1 minus negative 2 is the same thing as saying plus 2 is 1. And 1 plus 2 is equal to 3. And then I do my coefficients. So that 10 to the third comes down here. Now I can just say 9 times 6 times 9 divided by 3 times 3. These things cancel out with that. It's the same thing as saying 6 times 9. So 54 times 10 to the third, and don't forget your units, newtons. The proper way of writing this would then be 5.4 times 10 to the fourth newtons, but if you get this far, I'll be happy, right? So the whole point of scientific notation is that it makes it easier because really all I have are single digit numbers here, or close to it, and then I just have to worry about my exponents. I don't have to worry about counting zeros as I'm plugging it into my calculator or using the exponent function or whatever. Don't have to worry about any PEMDAS rules because it's all multiplication. And with this, it's just the exponent rule. So here's another example. 2 electrons are separated by a distance of 8 nanometers. What is the type and magnitude of the electrical force? So one thing that you have to note is that because they're both electrons, I have to find the charge. And the charge of many things is found on page 558 of your textbook. And that's 1.6 times 10 to the negative 19th coulombs. It's very small. And the distance is 8 nanometers, or 8 times 10 to the negative 9th meters. I always have to convert these to coulombs and meters. Well, the type is easiest. There are 2 electrons. You don't even have to remember that they're negatively charged. They are the same charge because they are the same charge. So because they're the same charge, it's a repulsive force. And then for the magnitude, I again just plug it in. This is your K value. These are both your Q values. And this is your R squared, and I'm just multiplying it twice just to make sure I don't make any mistakes. I take just the 10 to the whatever powers, and I use my exponent rule. So 10 to the 11th plus negative 19 plus negative 19 minus negative 9 minus negative 9 is equal to 10 to the negative 9th. And then I take just the coefficients. So 9 times 1.6 times 1.6 divided by 8 is 0.36. So my answer is 0.36 times 10 to the negative 9th, and don't forget your units as newtons, because that's the units of any force. I would rewrite this in proper scientific notation as 3.6 times 10 to the negative 10th newton. But again, if you get it this far, that's great. So the things to remember with Coulomb's law calculation, it's all multiplication and division. There's no addition and subtraction. Write out your R squared term as R times R. Do the exponent part first, and remember your exponent rules. If things are multiplied by each other, then you add the exponents. If they're divided, you subtract the exponents. And then do the coefficient part second. So remember your PEMDAS rules, meaning if you have 3 times 3 times 3, divided by 4, and then there's also another 4 on the thing, you have to either divide again by 4 or divide by the quantity 4 times 4. And then you combine these two parts and you add the units of newtons.